3D printing, also known as additive manufacturing, represents a revolutionary approach to fabrication. Unlike traditional subtractive manufacturing methods that carve away material from a solid block, 3D printing builds objects layer by layer from a digital design. This process allows for the creation of complex shapes and intricate designs with remarkable precision and efficiency. It offers a paradigm shift in how we design, prototype, and manufacture products across a wide range of industries, from aerospace and healthcare to consumer goods and art. Imagine holding a detailed model of a human heart, perfectly replicating its intricate chambers and valves, created not by hand but by a machine that prints it layer by layer using plastic or even living cells. This is the power of 3D printing, a technology that has rapidly evolved from a niche prototyping tool to a transformative force in manufacturing and beyond. Its ability to create customized, on-demand objects is reshaping industries and empowering individuals to bring their creative visions to life. The impact of 3D printing extends far beyond rapid prototyping. It is enabling the creation of personalized medical implants, lightweight aerospace components, and intricate works of art. The technology also empowers individuals to create customized products at home, democratizing design and manufacturing in unprecedented ways. The possibilities seem limitless as 3D printing continues to evolve and mature. From creating intricate jewelry to building houses and even printing human organs, 3D printing is pushing the boundaries of what's possible. As material science advances and printing techniques become more refined, the applications of additive manufacturing are only expected to expand further, promising a future where customized and on-demand production becomes the norm. This technology truly represents a paradigm shift in how we create and interact with the physical world. The conceptual roots of 3D printing can be traced back to the late 19th century, with early forms of photo sculpting and automated fabrication. However, the true foundation of modern additive manufacturing emerged in the 1980s. This era saw the development of key technologies like stereolithography, or SLA, and selective laser sintering, or SLS, which laid the groundwork for the rapid advancements we see today. These early innovations marked the beginning of a transformative journey in manufacturing. The 1980s witnessed a surge of innovation in the field of rapid prototyping, driven by the need for faster and more efficient ways to create product prototypes. Researchers and engineers began exploring various methods of building three-dimensional objects from digital designs, leading to the development of the first 3D printing technologies. This era marked the dawn of a new era in manufacturing, where complexity and customization could be achieved with unprecedented ease. As the initial technologies matured, the potential of 3D printing began to extend beyond prototyping. Researchers started experimenting with different materials and processes, expanding the range of applications for additive manufacturing. The early adopters of 3D printing recognized its potential to revolutionize industries ranging from aerospace and automotive to healthcare and consumer goods. The early years of 3D printing were characterized by experimentation and rapid development. Inventors and engineers pushed the boundaries of what was possible, laying the foundation for the diverse and sophisticated 3D printing technologies we see today. These pioneers paved the way for a future where additive manufacturing plays a central role in how we design, manufacture, and interact with the physical world. Charles Hull is widely regarded as the father of 3D printing, having invented stereolithography, or SLA, in 1986. This groundbreaking technology uses a UV laser to cure liquid resin layer by layer, creating solid 3D objects. Hull's invention marked a pivotal moment in the history of additive manufacturing, paving the way for the development of numerous other 3D printing processes. Carl Deckard's development of selective laser sintering, or SLS, in 1987 further expanded the capabilities of 3D printing. SLS uses a laser to fuse powdered materials like nylon and metals, enabling the creation of robust and functional parts. This innovation opened up new possibilities for 3D printing in industries requiring high-performance materials. The development of fused deposition modeling, or FDM, in the late 1980s by S. Scott Crump democratized 3D printing, making it accessible to a wider audience. FDM, which extrudes molten thermoplastic filament to build objects layer by layer, became the foundation for many desktop 3D printers. This accessibility fueled the maker movement and spurred further innovation in the field. These pioneering figures and their inventions laid the foundation for the rapid growth and diversification of 3D printing technologies. Their contributions have transformed manufacturing processes and continue to inspire ongoing innovation in additive manufacturing, pushing the boundaries of what's possible in design and fabrication. Several core 3D printing processes have emerged, each with its own strengths and limitations. Stereolithography, or SLA, uses a UV laser to cure liquid resin, creating highly detailed and smooth-surfaced objects. Selective laser sintering, or SLS, fuses powdered materials with a laser, producing strong and durable parts from various materials, including metals. Fused deposition modeling, or FDM, one of the most widely used 3D printing processes, extrudes molten thermoplastic filament to build objects layer by layer. This method is relatively inexpensive and accessible, making it popular for hobbyists and prototyping applications. Digital light processing, or DLP, projects images onto a vat of liquid resin, curing an entire layer at once, resulting in faster print speeds. Binder jetting uses a print head to deposit a binding agent onto a powder bed, creating a solid object layer by layer. This process is suitable for creating full-color prints and complex geometries. Material jetting dispenses droplets of photopolymer resin onto a build platform, which are then cured with UV light, offering high precision and material versatility. Each 3D printing process offers unique advantages and disadvantages, making it essential to choose the right technology based on the specific application and desired material properties. Understanding these processes and their capabilities is crucial for effectively leveraging the power of 3D printing in various industries and applications. Section 5. Materials in the additive manufacturing landscape. The range of materials compatible with 3D printing is constantly expanding, further broadening the applications of this technology. Plastics, such as PLA, ABS and nylon, are commonly used due to their affordability, ease of processing and diverse properties. Metals, including titanium, stainless steel and aluminum, are increasingly used for applications requiring high strength and durability. Composites, which combine different materials to achieve specific properties, are gaining traction in 3D printing. These materials offer unique combinations of strength, weight and flexibility, opening up new possibilities for advanced applications. Ceramics are also being explored for 3D printing, enabling the creation of intricate and heat-resistant components. Bioprinting, a specialized field of 3D printing, utilizes bioinks containing living cells to create tissues and organs. This groundbreaking technology holds immense potential for regenerative medicine and personalized healthcare. The development of new materials and bioinks continues to push the boundaries of what's possible in 3D printing. The expanding material palette for 3D printing is unlocking new possibilities across various industries. From lightweight aerospace components to customized medical implants and intricate works of art, the ability to print with diverse materials is driving innovation and expanding the applications of additive manufacturing. Section 6. Exploring the diverse applications of 3D printing. 3D printing has found applications in a wide array of industries, revolutionizing design, prototyping and manufacturing processes. In aerospace, it enables the creation of lightweight and complex components, reducing material waste and improving fuel efficiency. The automotive industry leverages 3D printing for rapid prototyping, customized parts and tooling. Healthcare is experiencing a transformation thanks to 3D printing. Personalized medical implants, surgical guides and prosthetic devices can be created with unprecedented precision and customization. In the consumer goods sector, 3D printing enables the creation of customized products, on-demand manufacturing and personalized designs. art and architecture are also embracing the creative potential of 3D printing. Intricate sculptures, architectural models, and even entire buildings can be created with this technology. The ability to realize complex designs and push the boundaries of creativity is driving the adoption of 3D printing in these fields. Section 7. The legal landscape of 3D printing. The rise of 3D printing has introduced new legal challenges related to intellectual property, product liability, and regulation. The ease of replicating designs raises concerns about copyright infringement and counterfeiting. Determining liability for defects in 3D printed products is another complex legal issue. Regulating the use of 3D printing for potentially harmful purposes, such as creating weapons or counterfeit goods, presents significant challenges for lawmakers. Balancing the need to foster innovation with the responsibility to protect intellectual property and public safety is crucial in the evolving legal landscape of 3D printing. As 3D printing technology continues to advance, legal frameworks must adapt to address the unique challenges it presents. International collaboration and harmonization of regulations are essential to navigating the complex legal issues surrounding intellectual property, product liability, and the responsible use of 3D printing. The increasing accessibility of 3D printing necessitates ongoing discussions and updates to legal frameworks to ensure responsible innovation and address the ethical considerations associated with this transformative technology. Balancing the benefits of 3D printing with the potential risks requires careful consideration and proactive legal measures. Section 8. Advantages and disadvantages of additive manufacturing. 3D printing offers numerous advantages over traditional manufacturing methods. It enables rapid prototyping, allowing designers to quickly iterate and refine their designs. Customization is another key benefit, as 3D printing can create highly personalized products tailored to individual needs. Reduced material waste is a significant advantage of additive manufacturing, as it only uses the material required to build the object, minimizing scrap and waste. On-demand manufacturing is another benefit, enabling the production of parts and products as needed, reducing inventory costs and lead times. However, 3D printing also has its limitations. The size of printable objects is often restricted by the build volume of the printer. The range of printable materials, while expanding, is still limited compared to traditional manufacturing. The speed of 3D printing can be a bottleneck for mass production, as the layer-by-layer process can be time-consuming for large quantities. The cost of 3D printing equipment and materials can also be a barrier to entry for some individuals and businesses. Section 9. The future of 3D printing. The future of 3D printing holds immense potential for further advancements and broader applications. Continued research and development in material science will expand the range of printable materials, enabling the creation of objects with even greater functionality and performance. Improved printing speeds and larger build volumes will make 3D printing more viable for mass production and larger-scale applications. The integration of artificial intelligence and machine learning will further automate and optimize the 3D printing process. 4D printing, which involves creating objects that can change shape or properties over time in response to external stimuli, is an emerging area of research with exciting possibilities. Bioprinting and the creation of functional organs and tissues hold transformative potential for healthcare and regenerative medicine. Section 10. Conclusion: the transformative power of 3D printing. 3D printing has emerged as a disruptive technology with the power to revolutionize design, manufacturing, and various other industries. Its ability to create complex shapes, customize products, and reduce material waste is transforming how we create and interact with the physical world. From rapid prototyping and personalized medical implants to on-demand manufacturing and intricate works of art, 3D printing is pushing the boundaries of what's possible. As the technology continues to evolve, with advancements in materials, processes and software, the applications of 3D printing are only expected to expand further. The democratization of design and manufacturing through accessible desktop 3D printers is empowering individuals to bring their creative visions to life. The future of 3D printing holds immense promise for solving complex challenges and driving innovation across various sectors. 3D printing is not merely a tool for creating objects, it's a catalyst for creativity, innovation and positive change. As we continue to explore the vast potential of this transformative technology, we can expect to see even more groundbreaking applications emerge, shaping the future of design, manufacturing and the world around us.